In this video, I'm going to introduce the elements of group 15. The elements of group 15 are collectively referred to as the Pnictogens, P-N-I-C-T-O-G-E-N, and S if you want to make that plural. And I think that's just kind of a fun word, and the only reason that I remember this is because P and N start the Pnictogens, and P and N also start group 15. Group 15 is the fourth column from the right on the periodic table. As such, all of the elements in group 15 have 5 valence electrons. So if the elements at the top of group 15 are going to make an ion, they're going to gain 3 electrons, gaining a -3 charge. That'll give them a noble gas electron configuration. But the elements at the bottom of group 15 are metalloids and metals. And metals don't tend to make anions. Metals make cations. And as such, you will tend to see ions with charges of +3, which would empty out the p subshell, the valence p subshell, and leave the ion with only completely filled or completely empty subshells. So if we look at group 15, we can see that we have a mixture of 2 nonmetals, 2 metalloids, and 1 metal. At room temperature, nitrogen is a gas, all of the rest of them are solids, and again we can see the density of the solids increasing as we work our way down the periodic table as the molar masses get bigger for each element. So the smallest element in group 15 is nitrogen. And if we want to draw a Lewis diagram for nitrogen, we see that there is a triple bond between the 2 nitrogen atoms. It's a diatomic molecule. And because that's a triple bond, it's an extremely strong bond. To take those 2 nitrogen atoms and completely separate them, you're going to have to break 6 electrons worth of bonding holding the 2 nitrogen atoms together. As such, nitrogen will only react if the result is going to be formation of a large number of relatively strong bonds. As such, nitrogen does react with metals, which will result in ionic lattices that have extremely large lattice energy. So in other words, if there's going to be very, very strong ionic bonds between the N3 anion that we would expect to form from the nitrogen and the corresponding cation that we would make from the metal. So we would be looking for cations with very high charge densities. For example, lithium, because while it's only a +1 charge, it's a very tiny, tiny little cation, or the cations formed from the alkaline earth metals like magnesium or calcium, for example. And so we don't see a lot of things reacting with nitrogen gas, but those that do react with nitrogen gas tend to give us energetically favorable products such as strong ionic lattices. And of course, if we're going to create an ionic product, we need to make sure that the charges of our cations and anions balance out so that we have a net neutral product. So we would need 3 lithium cations for every nitrogen anion. And that means that our balanced reaction would look like this. If we were going to write the magnesium reaction, we have a +2 charge on the magnesium and a -3 on the nitrogen. So in order for that to be neutral, we're going to need 3 magnesiums for every 2 nitrogens. There's no water around, that's an ionic solid. And to balance that